thank you very much for giving me a great opportunity here. I'm so thrilled to be here. I'm so honored to have a presentation in front of you. Thank you very much for this great opportunity.
Maybe you could get a little closer to the microphone.
Oh.
You need to be louder.
I can't do it. How to do it? Is it better?
Yes, yes.
Yeah.
Yeah.
So this is today's agenda. So first, I'm going to tell you my self-introduction, who I am, and what I have done before I came here. And next, I'm going to tell you the importance of building connection with you guys, patients. Why hearing patient stories matters. And then I'm going to talk about our research lab and lab members, lab institutions, mission of our lab and our research. And then I'm going to show you a specific research walkthrough, the journey of a research project. And lastly, we have a lot of challenges doing our research. So I'm going to show you the specific challenges that we face. All right, so the first, I'm going to start from my self-introduction and telling you the importance of building connection with patients. So this is my career path. So I graduated from Keio University School of Medicine, which is one of the prestigious universities in Japan, in 2011. And since then, I did a resident doctor, and I've been a chief resident, and I completed my residency and the chief resident. And since 2016, I have been a fellow in the Division of Cardiology at the Keio University Hospital. And from the next year, 2017, I started my research careers. And I entered the Graduate School of Medicine, Keio University in 2019. And I got PhD in 2022 with early completion. And 2 years ago, in 2023, I came here as a postdoctoral fellow in Stanford University. So this is my career path. And next, I'm going to tell you what I have done before I came here. So when I was in Japan, I was aiming to be a two-way player as a scientist. So you can see real two-way player here in the picture. So here is the Shohei Ohtani, Major League Baseball player. So he is not only a batter, but he plays as a pitcher very well. And actually, I'm wondering if it's okay for me to show this picture, because here is San Francisco. You are a lot of Giants fans, and there are a lot of anti-Dodgers fans. So, but yeah, please forgive me just showing this guy. So, what does the phrase two-way player mean in science? So actually, I've been working in both basic research and clinical research as well. So basic research is research focusing on more fundamental or basic, like elucidating the mechanism of disease, the onset of the disease. On the other hand, the clinical research is a research more related to the patients and medical management, medical treatment. So as a basic research, I did the research regarding the mitochondria. You can see the two yellow arrows here, and these arrows indicate mitochondria. So brain, heart, and muscles, these organs are filled with mitochondria. And if the mitochondrial function deteriorates, the organ function also deteriorates. When I was in Japan, I have focused on the mitochondrial function as a basic research. On the other hand, as a clinical research, I worked on studying the communication gap between healthcare providers and patients. So you can see this graph. For example, this graph shows the mismatch between patients' understanding of their prognosis of heart failure and what medical calculators predict. So yellow bar shows the consistent, their prediction of prognosis are consistent with the medical calculation. But the right bar, the blue and red bar, demonstrate the inconsistency of their understanding of their prognosis with the medical calculation. This finding suggests that patients' understanding of their heart failure remains insufficient despite education provided by medical providers. And this result highlights the need for greater efforts. We need to make more efforts to communicate with patients. So I'm going to show you a very, very interesting example of the difference of perspectives of two people. So you can see the guy is going out with a beautiful lady, and he thinks that everyone wants a ride in this great sports car like Ferrari or Porsche, whatever, and makes him feel like a Bond girl, doesn't he? So he thinks so, but she doesn't. She thinks, after spending an hour on my hair will become mess around. Seriously? So this is really interesting example. So we need to remember that whenever two positions exist, a difference in perspective is almost inevitable. Same thing happens in the between providers and patients. So this graph shows what matters to providers and patients. And some of the area overlap, but the pure red regions here represent what patients consider important, but not recognized by providers. And these areas are very important. We need to identify these areas, find the gaps, and we need to address these needs and solve these barriers. These are very important things. And so the origin of our research lies in the voice of patients. That's why hearing patient stories very matters. All right, so the topics has changed. Before I came here, when I was in Japan, I faced several challenges in conducting my research. One of them is diversities. About 98% of Japan's population is Japanese. So there is a lack of diversity in Japanese medicine. So I thought that I need to have a broader perspective. The second one is the scarcity of enrolled clinical trials. This table shows the number of in the national clinical trials that each country participated. The United States, you can see, ranked first, but Japan was all the way down 19th, ranked as 19th, which is quite unexpected. So the scarcity of enrolled the patients in the national trials is another challenge for me. The last one is the restriction of human samples. I put the number here. So this demonstrates the number of transplantation, heart transplantation in 2015, 10 years ago. The number of Japan's heart transplantation was 450. On the other hand, the number of US was 7,000. So it's totally different. And we obtained the human samples from transplanted organs, such as heart or brains. So the number of transplantation is directly linked to how many human samples we can obtain. This is one of our challenges that we faced in Japan. But here in Stanford, Stanford is one of the highest patient volumes. So many of patients in United States assembled to these institutions. And Stanford is a leading enroller in several clinical trials. As a matter of fact, now we have 7 or 8 clinical trials in our lab alone. So the number of clinical trials are totally different from Japanese one. And lastly, the Stanford University is building a biobank through organ transplantation. The number of transplantation conducted in Stanford was 85 in 2022. That is as the same as the total number of the heart transplant performed in all of Japan. So to solve my challenges that I faced in Japan, I came here to study in Stanford University. Alright, so next I'm going to talk about our institution and research lab. When you visit our homepage, you can see the mission of our lab. Here is our mission. So the homepage says that understanding the fundamental mechanisms of amyloid formation and deposition is our mission. And there are large 3 topics. The first one is establishing animal and cell models of amyloidosis. So, this is very, very important. So creating the animal or cell models, reproducing the disease, the phenotype, the symptom, because we need to first do the experiment using these animal or cell models. We can't use directly the human body in terms of safety or in terms of ethical problem. So this is very important to create the animal and cell models. The next one is identifying the mechanisms underlying the development of amyloidosis. There is no comment to add to this topic. And the last one is conducting the clinical and translational studies in amyloidosis. So it is very important to not only to do the basic science, but also to do the clinical research, and combining these 2 topics, identify the gap of the patients, and we can address the unmet needs or we can find the robust data. So doing the basic research and doing clinical trials and clinical medicine and combining these data or this knowledge are very important. Okay, so next I'm going to show you the lab members. The principal investigator of lab is Dr. Kevin Alexander. So he is a heart failure specialist and assistant professor at Stanford. He treats advanced heart failure, especially who require the transplantation of very, very severe heart failure and cardiac amyloidosis, especially the transthyretin amyloidosis. So he got a lot of support from NIH, AHA means the American Heart Association, and some drug companies to conduct his research. Yeah, actually I thought he came here today, but I can't see him. It's a little bit sad for me. And next is myself. I have already introduced myself, so please I will skip that here. And next one is the Dr. Garcia. She earned her medical degree from the American University of Beirut and conducted research on metabolic syndrome. As a postdoctoral scholar at Stanford, she published quite a lot of publication articles regarding the ATTR amyloidosis in top journals. And she will begin her internal medicine residency at Yale University from this summer. The next member is Miss Nishwan. She is a life science research professional. She earned her BS in neuroscience, and she has experience in retinal neuroscience research and cardiovascular genetics. Since 2022, 3 years ago, she was supported our lab and assist our team with experiment preparation. She is now completing her master's degree and plans to pursue a PhD in molecular biology and neuroscience. The last member is John Isaiah Jimenez. He is also a life science research professional. He studied biochemistry and he conducted a research on metabolism and joined the Stanford cardiovascular summer program to study hepatic enzyme. At the summer program, he met with Dr. Alexander Kevin, and 2 years ago, he joined our lab. He plans to pursue a career in medicine, combining patient care with a passion for research. So these are our members, and we are all closely linked and working toward the common goal of elucidating the amyloidosis. So next, I'm going to show you a specific workflow, the journey of a research project. So this is the first step, the phase 1. The phase 1 is first the framing clinical questions based on the patient care. As I mentioned earlier, identifying gaps in medicine, uncovering unmet needs, and asking the right clinical questions. These are very, very essential. And they represent not only a critical step, but also the true starting point of our research. And daily patient care is very important because these patient care reveal gaps in knowledge or unclear decision points. it is also important to listen to patients' experience in order to enable us to help identify unmet needs. So, framing clinical questions is the first step to start a research project. The next phase is establishing the registry and biobank. So I put here the estimated timeline. So it takes a little bit time to establish a registry or biobank. It takes about 1 to 3 years generally. And we collect comprehensive patient data to support translational research. And we also store the biological samples, such as transplanted heart tissue, to enable molecular analysis and future discoveries. So this phase is like a preparation for specific experiment and analysis of the database. Now, this is the main phase of our research project. The phase 3 is elucidating disease mechanisms using animal and cell models. Estimated timeline is about 5 years. So, reproducing disease phenotypes in experimental system to uncover underlying mechanism is very, very important. And we identify the therapeutic targets. To explain more, if we can establish clinical models reproducing the disease the symptom, we can identify the underlying mechanism. But beyond that, these models allow us to test various drugs and treatments to inhibit those pathological processes. In other words, these models not only help us understand the underlying mechanisms, but also serve as a platform for discovering the effective therapies. This is the phase 3. And the next one is the phase 4, translating science into solutions. Estimated timeline, I wrote that it's about 5 to 10 years, but some scientists says that it takes 20 or 30 years. So, translating the scientific findings into potential therapy for clinical use. This is the goal of the research project. To do it, collaborating across disciplines to develop treatments that address unmet medical needs are very important. Alright, so these 4 steps are the journey of a research project or workflow, and I'm going to show you the latest data which was published the end of last year. So the project was about the mouse model we have created regarding the ATTR amyloidosis. This project was conducted mainly by Xiaokang Wu. She was a former postdoc here in Stanford chemistry lab, and she got married and moved to Michigan to be with her husband. So she left our lab a year ago. Alright, so this mouse was created by first removing the mouse TTR, natural mouse TTR. We removed the mouse TTR and then replaced the human bat TTR instead. Why we removed the mouse TTR? Because it is said that the mouse TTR sometimes inhibit the human TTR, stop the human TTR function. So we need to first remove the mouse natural TTR. and then replace the human bat mutant TTR. And this mouse model interestingly shows that the higher human TTR level in the blood serum, and when we take a look at the electron microscope, this analysis demonstrated that there are quite a lot of amyloid fibrils in the mouse heart. We did a genetic examination for this mouse model, and CXCL1, 2, 3, and CCL20. It's a little bit the expertise jargon, but they are very important for inflammation markers. So this model, this project suggests that inflammation plays a very and critical role in ATTR pathology. So this is our latest data, which was published the end of last year. One thing I'd like you to remember, or I'd like to emphasize, is that there's no final goal in this cycle. Once we reach phase 4, we need to return to phase 1 and ask patients, how effective was the drug we developed? How well did the new treatment work? So it's a continuous process of learning and improvement. The important thing is to keep the cycle going. Alright, so lastly, we have a lot of challenges in conducting research here in Stanford University. I'm going to show you the specific challenges. In the first phase, the challenges is sometimes it's really difficult to find clinical questions. But finding the clinical question is the first step of our research. So this is essential and indispensable. This is very, very important things. So in order to overcome or solve this problem, we need to commit to medical management, and we need to listen to all voices. The challenges in the next phase, phase 2, is gaining support. The first is the patient cooperation. Patient cooperation is, of course, essential and indispensable to do our research. So it is very important to engage patients in research. And we need a lot of money to build our database or build a biobank, establish a biobank, and conducting the clinical trials. So securing grants, fellowship, and finding opportunities are really essential. So the challenges in the phase 3, this is the biggest challenges for us. So I wrote with a red color the unique complexities of amyloidosis. So the former greatest scientists have tackled this disease, the amyloidosis, but as a matter of fact, nobody has elucidated the underlying mechanisms. So this suggests that the difficulty of elucidating the amyloidosis mystery. In order to overcome or solve this challenge, the first we need to think. We can't stop thinking. And communicating with other societies can sometimes help us find a key or find a hint to solve our challenges. So communication with other societies are also important. And of course, try and error. This is very important. The success rate of science is very, very low. It's less than 10%, like a baseball. So we need to do try and error and never give up. And the challenges in the last phase is the hurdles in implementing findings into society. But fortunately, here is Bay Area. There are very great innovations, startups, so we need to take advantage of this great environment. And collaborating with pharmaceutical companies is another essential solution. So these are what kind of challenges we face and how we solve them. And lastly, I'm going to talk about the meaning behind our research. So previously, I told you that understanding the fundamental mechanisms of amyloid formation and deposition, this is our mission. But this expression is more appropriate for a professional or academic audience. Have you ever heard about the Nature Cell Science? So these are top journals. These are very, 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 very great journals. And every single scientist, including me, are aiming to publish these top journals. But one thing we should know is that these top journals tend to focus mainly on phase 3. And they don't pay much attention to whether the scientists actually move forward with implementing their findings. The scientists move forward to phase 4 or not. That's why I want to emphasize. So many researchers, even after publishing in these top journals, stop at phase 3 and never progress to phase 4. They feel satisfied with the publication alone without taking the next step toward real-world impact. But as I mentioned earlier, to keep the cycle going, this is important. So again, I need to emphasize that phase 1 marks not only the beginning, but also the ultimate goal of our research. So, like today, your voice very, very matters. Alright, thank you very much for your listening. So now a Q&A?
Yes, Q&A. This is your opportunity to ask him everything you ever wanted to know about research and why it takes 30 years.
I'm so nervous.
Well, I have a question.
Yes.
You talked about the different amount of years in each phase, but are there any overlap between the phases, or you have to complete one phase completely before you advance to the next one?
Yes, thank you very much. This is very great question. So,
Would you repeat the question, because we're taping this,
okay.
and they may not have heard it. Thank
So
you.
she asked about whether these phases are sometimes overlap or not, and the answer is yes. So each phase is not completely separated. They're always overlapped, and sometimes we go to the phase 3 and go back to phase 2 and go to the phase 3, go and back again and again. So these phases are overlapped, and sometimes we go back, we go forward like this.
So it's possible that it could be faster time frame or even slower because you go back and forth.
Yeah, so that's why it takes a lot of time. Yes, please.
with technologies like artificial intelligence, do you see that that has the potential to speed the process up?
So he asked about the artificial intelligence can make some progress of the amyloidosis diagnosis or something like that.
Yeah, or just the research process.
Yeah. So yeah, of course, the AI could help our doing the research, and not only for research but also the diagnosis as well. So I will tell you one example. So I'm not familiar with the U.S. the amyloidosis diagnosis, but in Japan we sometimes use the biopsy to make diagnosis of amyloidosis. But the success rate of biopsy that we pick the area that includes the amyloidosis is 50% or something like that. And if we fail to pick up the amyloidosis area, even though the patient has amyloidosis, we say it's a negative data. But when we use the artificial intelligence, we shouldn't, for us, it looks like the negative data, but AI can identify it's a positive data. We can correctly make diagnosis for these patients. So in this area, I think the AI could help us. Yes, please.
When do you make the decision to research into a cure for a disease versus a treatment for a disease? When do you make that call in your cycle to decide maybe this is not a solvable illness, but we'd be better served to get more treatments out there to better assist the patients, or vice versa? When do you make that, or do you make that decision?
Sorry. So your question is I don't know the difference of the cure and treatment. You asked about that?
Well, just, you're deciding in your research cycle which direction you want to go, right? That when you start out, you want to solve ATTR amyloidosis, right? When do you decide that you're going to try to solve ATTR amyloidosis versus creating a treatment for ATTR amyloidosis? At what point does that show itself to you that, maybe ATTR isn't curable, we're better off making treatments, or maybe it is curable, but it's gonna take so much of our time that we're not gonna be making treatments to help patients?
Yeah, thank you very much. So, yeah, it's a
Is that too confusing?
Yeah, it's a very difficult question to answer, but it's a personal opinion for me that for me the ultimate goal is first the creation of the treatments. So this is my ultimate the goal, and to get the ultimate goal, achieve the ultimate goal, the elucidating the underlying the mechanism is just on the path of my goal. So I don't think which is first or which is not first. So I'm going just aiming the ultimate goal.
For treatment?
Yes. Yes, please.
Are you ever able to use human amyloidosis samples, or is it always just mice?
So when I was in Japan, I used only mice or cell models, and we can't get the human samples. That's why I came here, Stanford University, US, and here we can use the human samples. So now I use the human sample here. Yes, please.
I don't know if you feel comfortable answering this, but I imagine that there's a lot of fear going around since the administration has changed. Is there a water cooler conversation that gives you the feeling that people in the research community are afraid of losing funding for things like this?
You mean the administration is the change of the political policies or
Yes.
something like that?
Yes.
Yeah, we are so anticipated about it, and so I have been here just only 1.5 year, but the policies has changed drastically in these half years. So I'm not familiar with deeply familiar with the medical systems or funding systems in US, but this is very very great issue for me and for us, for our lab. Yes, please.
Can you expand on the current research project that you mentioned that was done in mice where you linked inflammation to ATTR, I think you said? Just what the findings were and what, like, just more info on that?
Yeah, so she asked about we can deeply focus more on the inflammation in ATTR or something, see this disease or not, and actually that mice model demonstrates the inflammation is very important for a process of amyloidosis. But we need to delve into more and more research more and more because just only saying the inflammation, there are many types of inflammation. So we need to figure out what kind of inflammation is upregulated in this mice model, and we need to find out whether the human samples have the same result or not.
So did the research show that inflammation was driving ATTR? Is that what the project was?
Yes. So this is a little bit difficult question. So inflammation can, of course, occur the ATTR deposition, but ATTR deposition can also occur the inflammation. So we don't know which is the first. My personal opinion is the ATTR deposition makes the inflammation upregulated. But we need to test and we need to prove my hypothesis. So this is our next project. Thank you very much for your question. Yes, please.
You talked about first having to think of the questions, and a lot of funny images come to mind with a bunch of brains sitting around going, oh, what should we ask? Where are your questions coming from? Are they coming from doctors who treat amyloidosis, only researchers who work in it, patients who have some really valid questions? Where are they coming from? And then how do you put them together to make a decision?
Okay, so it's a very difficult question to answer. Yeah. So listening all voices is like more conceptual for me. But I'm gonna take one example. So if the patient comes to our outpatient clinic, our assumption is a patient have some the difficulty of breathing or something like that because their cardiac function is very very bad. But actually the patient says that I feel a numbness of the limb. This is very very hard for me, and this shows the difference of the perspectives. So doctor thinks that the cardiac function is their first priority, or focusing on just only the cardiac symptoms, but patients focusing on more the neurological other symptoms, and other symptoms matters for patients. So, and as we see many patients, these voices are accumulated, and we know we identify the gaps. So this is the first step, the start over research working. My answer is right. Yeah.
And you see patients?
No, not here.
No, just, you just.
Yes, I have not gotten the U.S. license here, so I can't see patients. But I joined the Dr. Kevin's outpatient clinic, like shadowing, and also his outpatient and inpatient ward service. Yes.
How many clinical trials are being carried out at Stanford right now, specifically for amyloidosis?
We are doing the 8 clinical trials now, so the amount is very, very high. Yes, please.
So my question is, a question that we've had for many years. And the question is, and I think it even came up again today, is why is it that so many of us, and it's a lot, have been very athletic for the years, ate very well during the years, did the right things over all the years, and end up with amyloidosis. So is there much research being done on why amyloidosis happens in certain people?
So your question is why amyloidosis happens to some
Some of us and
some
and
certain
not.
people.
Especially with regards to some of us are very active, and over the years I've heard this, it was brought up again today, many stories about people that are very active in life and ate very well in life, and somehow end up with amyloidosis.
Yeah, this is ultimate question for me, and yeah, now I can't have a right answer to your question, but I'm really curious to know what kind of background so amyloidosis is important, and some the scientists or cardiologists says that the people who was very active, people who are very active like the sports players or athletes, sometimes can become have amyloidosis, and I think this is one of the key to solve the background mystery of amyloidosis. But I don't know how to test or prove this. We need to do a clinical, basic clinical the research to investigate the background of the amyloidosis.
So how much research, not only with Stanford, but other facilities, other medical facilities, like maybe perhaps Mayo, Boston University Medical, are there any other institutions where there's an emphasis on what causes it in patients? Therefore, it would eliminate the need for medications or drugs or CAR T cells or transplants. That's always been a thought in my mind is, have they zeroed in on what's causing it to try to prevent it from happening in others?
So my understanding is that each facility conduct the clinical research, but the collaboration with each facility is not sufficient even here in US. So as a tertiary system of amyloidosis here at Stanford University, so we need to collaborate more and more with other high facilities or tertiary facilities to identify the background, the mystery of the background.
I just want to say something that speaks to what Dina was mentioning about the questions that you ask when you start off research and getting perspectives in a diverse way from different specialists who deal with amyloid patients and how important it is, and especially getting the feedback from patients who live with this every day. Functional capacity, I heard too, when you mentioned everyday activities, is the first thing that patients that I've talked to say they realize that's the problem. There's a problem here. But there could be a lot of underlying things that a doctor that they go to is looking at as well. So I think it's important when you say diversifying your research and looking looking at all avenues is very important when we talk about this disease, because it's multi-systemic. It's not just a cardiologist treating these patients, it's a neurologist, it's a hematologist, it's an oncologist treating these patients. And I think that's the challenge, is bringing them all together in a way where things can be found and listened to and then translated, because you did say that was a gap. It's the translation of what you see in the lab through that mouse study and how we can help patients to get treatment that will heal them, that will cure them. I mean, ultimately, we want to cure disease. That's a goal, right? But it takes a long time to do that. Sometimes it takes many lifespans to understand that.
Yeah, thank you very much for your comments. Yeah,
Yeah.
I agree completely with you.
Yes.
Yeah.
Any more questions?
You can ask personally.
You have a room full of patients and caregivers here. What questions do you have for them?
Oh. Yeah.
Look, like what Tony was saying about how it seems like a lot of people who had very active lifestyles and ate well and took care of themselves, they're the ones coming down with it. Is there some like survey or some kind of, place that patients can give their backgrounds and that information can be collected, and maybe that would be a situation where my sister was suggesting AI could help, right? Could look at all those backgrounds and try to find some correlations, right?
Yeah.
Well, I know just even getting amyloidosis on your death certificate, should that happen and you happen to succumb from one of the side issues created by amyloidosis, getting amyloidosis on the death certificate so they're at least tracking what the numbers are is very difficult. And, we've had patients here with that issue. They ended up, because they had to have a heart transplant, they were on suppression drugs, ended up with cancer. The cancer is what ended up killing this person, and they wouldn't put amyloidosis on the death certificate because it was the cancer that killed it. But the cancer would not have happened had the heart transplant not been needed, and amyloidosis not attacked up the heart.
And I think, Dina, you experienced that with Bill.
I did. When my husband passed, it was a kidney failure because he had stopped dialysis. He had reached a point in life where he was done. And the person, my next door neighbor, was the one who ran the mortuary, and he said, I'm gonna call the doctor for the death certificate. And I said, you tell that doctor she will put amyloidosis. And so his death certificate came back, kidney failure primary kidney failure due to secondary amyloidosis. So you can ask for it, and you can get pushy with it if you have to.
This isn't a question for you, but it kind of piggybacks on what you were saying. What causes it? I don't know if anybody else here is a Vietnam veteran, but but we have found out that the Veterans Administration automatically accepts responsibility for the disease, AL anyway, I'm not sure about the other, AL amyloidosis, if you served in Vietnam.
Agent Orange.
Agent Orange.
In Vietnam.
So we're in the process of filing a claim, which probably now is slowed down to a crawl.
So this is, my point of the question too, is the fact that here is pretty much a clear identifier what caused the amyloidosis. Is it possible the rest of us who didn't serve in the military or were not exposed to Agent Orange, is there some kind of compound chemical that is perhaps the culprit behind this? I'm sure that's the question that many of us have had over the years.
So, I'm sorry,
What I'm saying is that it's a clear example that the government feels that Agent Orange in particular from Vietnam, I believe is what I understood, is there have been some, over the years, some veterans, men women who have served and were exposed to chemicals such as Agent Orange, and some all ended up with amyloidosis. And now that obviously for the government to approve that, it's a big thing.
Right.
So, but there must be other causes that are
Yeah,
somehow
because-
related,
right.
because there's a lot of us who didn't serve in the military, yet we get amyloidosis, and we're exposed chemicals or what have you, and I'm just wondering if, again, if there is really enough, research going on, you know, to try to figure that part of it out, so that we could try to lower the amount of patients with the disease.
Yeah, this is a very, very difficult question to answer, but so,
Same thing with cancer, right?
yeah, exposing the chemicals or something like that, so we need to make more importance of the each clinical research. So this background is probably not the over the world. It's more focus area. So in that case, we need to take more importance of each the clinical research. But at the same time, we need to collaborate and accumulate the patients' data to find out the important background of these diseases.
That's why it's so frustrating, that's the word, should be the word and emphasis for this disease. I have friends that call me and they say, come on, let's go for a walk. Well, I just about got out of bed, you know, and I'm walking, and I'm very unsteady, and the last thing I wanna do, you can't exercise your way out of this.
Right.
I talked to the doctor about dieting, other than low salt, which I understand, and I'm sure there's other things, I don't think you can die, I mean, it's a very frustrating, you know, you get sick and you get better. You go to rehab after you get a bad knee or leg, and leg gets better. I had a hip replacement, you know, a week and a half later, I was out running, no problem. This is totally different. And I think I'm hoping that the research will, as somebody mentioned, sorry, get to, you know, some other way to deal with this other than just medicine. I personally hate medicine. Nobody loves it. To me, less is better. If I had my druthers, I'd go off all of it, except the truth. No, but seriously, I don't know what's going on with that medication. I have no clue, you know? And it's just very, I'm glad there's guys like you out there in these groups. And I know my Dr. Wattilis is very involved with amyloidosis at Stanford, you know him? Yes. Very, you know, others are very, very focused on this one thing. It's a little late, but better late than never. But I know when I was diagnosed, I could have had this for years. And I had COVID and thought we had long-term COVID. That's the same symptoms. And that's when I got lucky. They tested me with echocardiogram and banned me. Otherwise, I'd be dead, but they would never found it. I have a cousin who had the exact same thing. It's not hereditary, it's just by coincidence. He went to the hospital. It was so bad after 2 years of being miserable and died by being tested. Never had a pill. Never had the luxury of the truth. So there's a lot going on, but it's very frustrating. And I'm 80 years old. I mean, I don't have, you know, 30 years to get better. So I'm not trying to be negative, but and that's why you gotta be proactive.
Right.
These medications, and make sure you get them, but again, not overdo it. I don't know what
Yeah.
I'm saying, I'm just.
Yeah, thank you very much for your giving me a very important comment. Yeah. Yes.
Yeah, to that point too, the whole, problem with amyloidosis is the misfolding of proteins. Shouldn't that be the focus? Why are these proteins misfolding? Is that a focus of research?
So yeah, many scientists focusing on the mechanism of the unfolding, misfolding the protein. But this is my personal opinion. That how can I say the shape of unfolding or the cause of unfolding is very, very important, but not the ultimate trigger of disease. because when we focus on the ball study met, this is one of the famous mutation, but this mutation has two types: the late onset of the ball sediment and early onset of early sediment. So there are two types, and these two types, the phenotype of these two types are totally different. So misfolding the protein is of course the trigger of disease, but not only this the characteristic, but also the background, patient background is very important. That's why there are two types of the late onset and early onset of ball sediment. They want certain mutation. You know what I mean? So I'm so sorry, my English is complicated.
Is that what your research is studying, early and late onset?
So yes, so most of the scientists are focusing on the misfolding the protein. So misfolding protein is very bad. That's why the amyloidosis happens. But my understanding is not the same. My understanding is first misfolding happens, and then some kind of patient background, and these two characteristics happens, then amyloidosis happens. This is my understanding.
Well, my understanding that drugs like Atruvi, that's part of their deal, is, I'm doing layman's terms, to stabilize, so that this unfolding doesn't continue. They haven't been able to figure anything out for what's already happened. That's my understanding. That's the next stage to make it better. Doesn't, have a thick heart, it's not gonna get thinner, but at least to maybe get somewhere with the amyloidosis that's already in there, but to stabilize it, which is why 4 years later, I'm definitely no worse than I was the day I started, if not better. Because otherwise it's progressive. So I think that's another direction that these medications are terrific in. And so that's a good thing. People prior to us didn't get 20 years of amyloidosis.
Yes.
Another question. In a facility like the Alexander Lab, where you've got projects going on, do you, as a full entity, research entity, connect with and interact with other research centers who are doing similar or even potentially the same amyloidosis research?
Yeah.
Boston and.
Actually, our lab has developed in these 2 or 3 years. So we are planning to collaborate with other facilities or other research lab. We have not yet done it.
No competition there?
No, no competition. It's okay.
Any more questions?
Yes.
A lot of these research are based on using mice. Why is that? Is there another animal that could work as well or differently?
Yeah, so first is it is said that the genetic background of mice are very similar to human. Yes. And next is, of course, the mouse is not so big. So it's, I don't know, it's alright to say, but it's really a little bit easier for us to conduct the using the mouse compared to the monkey or gorilla, chimpanzee. They're very, very big. Sometimes they fight me. But yeah, this is very interesting question.
Questions, guys?
Okay, what are
Okay. Everybody.
What happens if
question.
the mouse dies and you're in the middle? Do you have to start all over, or can you start from where you ended with the mouse that died?
When you end?
Yeah, say you have, I don't know how many mice you use, but say you're using 2, and one dies in the middle of your trial, whatever your start the research all over from the beginning with that, or do you continue where
I-
you were with those?
This is different from, yeah, it depends on the researchers, but I want to start from the scratch. Yeah, because we don't know the cause of death. First, but first we should investigate why the mouse was dead first, and if we find the cause of death, we need to redo the same project, the reason. We do the experiment from the scratch, 2 or 3 mice.
That's another reason why it takes so long.
Yes.
The only other question I had too is, you mentioned in that your colleague, your postdoc colleague that's no longer with you, in that experimentation, she was able to extract the bad TTR and put in human TTR. How did she do that?
So.
I mean, because if it's that easy, then why in humans you can't take out the bad
Exactly.
TTR? You know what I'm saying?
Exactly.
First, remove the mouse TTR. We use genetic the process. Have you ever heard of CRISPR
Yes.
Cas9? So like that, we use to cut the mouse the TTR in genetics and remove it, and then we insert the same using the CRISPR Cas9 and bat TTR, human TTR instead.
Gotcha. So then the mouse's body would reproduce the new Cas9 segment of the RNA in order for it to continue to make.
Continue to produce the human TTR,
Gotcha.
frequently to I.
Gotcha.
Yes.
So you changed the genetics of the mouse
Yes,
essentially?
yes.
Got
Not
it.
me, but yeah, the
Yes,
form.
thank you for that.
Yes.
I know the lab has been in existence for several years. I think it started with Dr. Lau, right?
Yes, Liao.
Liao, yes.
Liao.
Yeah, okay, yeah, and she did speak to us once, she was
Oh,
wonderful.
really? Wow.
In the, I'd say, I don't know, 5 years, however long it's been in existence, has there been any breakthrough or revelation, like an aha moment in your research of the entire lab during this time?
Entire lab. So, our biggest breakthrough was, of course, the creation of the mice model. Actually, all over the world, there is no great mouse model of ATTR amyloidosis, and I told her how to create the mouse model. It seems very easy. It just cut the mouse model, mouse TTR, and insert the human TTR, but it's very, very difficult. It was very, very difficult, and sometimes Lolly gave us some great advice in order to create these mouse models. So our biggest breakthrough was the creating that mouse model.
But nothing in terms of the disease itself.
Disease itself, yeah. So perhaps I think this is the next step. So without the mouse or cell model,
Mhm.
we can't analyze
Right.
the disease phenotype or disease background. So we have just begun.
Thank you.
Hi, yes, please.
This is a more personal question, but what made you want to research this?
Good
Wow.
question.
So this is very great question. So when I was in Japan, like a young doctor, I have treated many patients. But if I treated 100 patients, there are one patient who is not the same as other patients. So I remember one girl. So most of the Japanese patients with cardiology is about 80 years old, 90 years old, but she was 27-year old. I don't know why, but she got heart failure, and unfortunately she was dead. And that one case captured my heart. Why that young girl had such a very, very severe heart failure. Despite her lifestyle was very, very nice, there was nothing bad she was doing. And after that case, I considered I want to start my research project. I want to elucidate why such girl have a very, very severe heart failure. This is my start of my research.
Looks like maybe we're all finished with questions. And I can't thank you enough for agreeing to do this and Kevin for finding you for us. We appreciate that so much. We invite you to stay and listen to the pharma folks,
Yes.
when they talk about, clinical trials and what's going on with them. And also, we do need to take, I have to give them a health break. So we need to take a break of, 10, 15 minutes so you guys can go, do that, come back, get some more food.